What is going on, everyone? Welcome back to another video. Today we are going to be doing a steady state thermal analysis, the conduction through a solid plate. Let's get into it. So what is thermal conduction? Well, thermal conduction is one of our three modes of heat transfer, which describes specifically the transfer of heat energy within a material or between materials that are in direct contact with each other. Now, what do we mean by material in this description? We are referring to solid materials. If there was a gas or a liquid involved in the heat transfer, this would refer to our second mode of heat transfer, otherwise known as convection heat transfer. And our third mode of heat transfer is radiation heat transfer, which refers to the transfer of heat through electromagnetic waves. But today for this tutorial, we are going to be simply focusing on the conduction heat transfer through a solid plate. And this heat transfer results from the collisions and movements of the particles within the solid plate that transfer kinetic energy between the particles upon heating. The rate of thermal conductivity through the plate depends on the thermal conductivity K, which is a material-specific quantity. So a material with a higher thermal conductivity will transfer more heat effectively. Thermal conduction can be further represented by the diagram that we can see in the middle of the slide here. On the left-hand side of a conducting solid, we can see that we have a cold environment, T1. And on the right-hand side, we have a warm or hot environment, T2. And as a result, these two different temperatures will cause a temperature gradient over the solid, which in turn induces a heat flow, and thus heat can be transferred from one plane to the other. The governing equations for this analysis is Fourier's law, which describes the total heat transferred through the plate is equal to the negative times the thermal conductivity times the cross-sectional area times the temperature gradient, which for a linear distribution is equal to the difference in temperature over the thickness of our plate. We can further alter the equation to find the thermal resistance, RT, which is simply 1 over the thermal conductivity. And this just makes it so that we can draw comparisons between a thermal system and electrical system, where the thermal resistance would be analogous to the electrical resistance of an electrical system. So the analysis that we are going to do today is going to be a thermal conduction analysis through an aluminum plate that has a thermal conductivity of 151.55 watts per meter Kelvin. This plate is going to have dimensions of 1 meter by 1 meter by 0.1 meter, and the temperature on the right-hand boundary is going to be specified as 50 degrees Celsius, and the temperature on the left-hand boundary is going to be specified as 22 degrees Celsius. Now, as we are going to see in Ansys, the thermal conductivity varies as a function of temperature. Therefore, for a different temperature, we're going to have a different thermal conductivity. So the 151.55 that we have calculated here is the average thermal conductivity over a plate that has a temperature on the left-hand boundary of 22 degrees Celsius and on the right side of 50 degrees C. The images on the right-hand side here show the results that we should be getting from Ansys, and the calculations down here are going to be used in order to validate the results that we are going to get from Ansys. So based on all the information that we've provided in this problem statement, by plugging it into Fourier's law, we can calculate the total heat transferred through the plate as negative 42,435 watts. So when we run the analysis in Ansys, we should see that we have a temperature gradient through a plate that is respecting the boundary conditions. And we should see that the total heat transferred through the plate is consistent with the calculations performed from Fourier's law. Now, with a basic understanding of what thermal conduction is and the expected results that we want to see, we can go ahead and jump into Ansys and start building this simulation. Now with Workbench open, we can go ahead and start our simulation. In the middle here, we have our project schematic. This is where we are going to build the simulation. And on the left-hand side, we have the analysis systems that we can use in order to perform this analysis. And we are going to be taking the steady state thermal analysis system and dragging it into our project schematic. the first thing that we're going to want to do is to specify what our material is going to be. From our problem statement, we said that we are going to do this analysis for an aluminum plate. So we're going to go ahead and double click on engineering data right here. And this is going to open up a new tab called engineering data. We can see that we have a project tab here. So if we press this, we're going to go back to our project schematic. And if we press engineering data, we go to the engineering data of the thermal analysis. In order to add a material to our analysis from Ansys database of materials, we'll go ahead and press on engineering data sources up here. And then this opens a whole bunch of libraries that we can use to select a material from. We're going to go ahead and press on general materials right here. And in the second window here, we can see that this has opened up a whole bunch of materials. And we can see the second material here is aluminum alloy. So in order to add it to our analysis, we're going to go ahead and press on the plus sign here. And the little book appears here, shows that the material has now been added to our analysis. So now you may be wondering why I chose aluminum for this analysis. Well, if we go ahead and press on aluminum alloy, we can see our properties for the aluminum alloy down in this section down here. And we can see that we have the isentropic thermal conductivity available to us in the form of a graph that comes in Ansys's library of materials. So if you were to pick another material in order to perform this analysis, or if you wanted to specify your own material, you would have to make sure that the material that you choose or the material that you initialize for your analysis has this parameter, because this is the parameter that's going to drive the simulation. As we stated, it's a material specific parameter. So for a different material, a different amount of heat is going to be transferred through it. So now that we've added aluminum alloy as a material into our analysis, we can go back to our project tab by pressing on project. And now we can see that we have a check mark beside engineering data. We actually already had a check mark beside engineering data because by default, Ansys always has us using structural steel. But as we go through the mock-up of this analysis, you'll see that these question marks are going to slowly turn into check marks, meaning that we've completed the section. So next up is geometry. As you can see, we have a question mark here. So we need to build our geometry for this analysis. So let's double click on geometry. And in the bottom left-hand corner here, it says starting SpaceClaim. So I'll wait for SpaceClaim to open in order to build our geometry. Now with SpaceClaim open, we can go ahead and start building our geometry. The first thing we're going to do is end sketch editing, because by default, SpaceClaim has us sketching on the ZX plane. And personally, I don't like sketching on this plane. I prefer sketching on the YX plane. So we're going to press on end sketch editing. And before I do anything, I'm going to check my units to ensure that my units are going to be the same and consistent all the way through my analysis, to ensure that I'm not going to run into any magnitude errors within unit conversion. So the first thing that I'm going to do is I'm going to press on File. I'm going to press on SpaceClaim Options. This will bring up this window here. If I press on Units, we can see that the unit length used in SpaceClaim is millimeters. However, when we go to the meshing stage and further, we'll see that meters is the preferred unit used by Ansys. So I'm going to go ahead and change this unit to meters to make it consistent. And now I'm going to press OK. And now our SpaceClaim environment has been changed to use meters instead of millimeters. So now we can go ahead and sketch the plate that we want to do our analysis on. So I'm going to go ahead and press sketch mode. I'm going to hover over the XY plane. I'm going to press on the Z axis down on the box here to make it normal to the screen. And I'm going to choose my rectangle command. I'm going to snap it to the origin by clicking. And I'm going to drag out the rectangle. I'm going to specify the first length to be 1 meter, and I'll press Tab to go to the second length, and I'm going to type in 1 meter again, and I'm going to press Enter in order to confirm this 1 by 1 meter rectangle. This will be used as the sketch for our 3D solid. So we can go ahead and press on End Sketch Editing. And now if we put it into an isometric view and choose the pull command and use our sketch that we've created, we can now pull the solid out. And I'm going to specify the thickness of our plate to be 0.1 meter to make it consistent with our problem statement. Press enter. And now we can see that I have a plate of 1 by 1 meter and a thickness of 0.1 meters. Now with it sketched in SpaceClaim, I can go ahead and close SpaceClaim, and all the data will be saved in our workbench. And now, as we can see, we have a check mark beside geometry, meaning our geometry is ready to go. Next up, we are going to specify the boundary conditions for this problem and run the analysis to get the results that we want. So to do that, I'm going to double press on model. And as we can see, it says starting mechanical. So I'll wait for that to load. Now with mechanical loaded, we can go ahead and specify the mesh that we want to use, initialize the boundary conditions, and run the simulation to get our desired results. But before we do any of that, I'm going to go ahead and make sure that the material that I'm using is okay, because as I mentioned, the default material that Ansys likes to use is structural steel, but we wanted to do this analysis for an aluminum plate. So to do that, I'm going to go ahead and press on the plus beside geometry, and I'm going to press on the solid, which describes our solid plate here. And as we can see, the material assignment is structural steel. I wanted aluminum, so in order to change that, I'm going to press on structural steel. I'm going to press on the little triangle that appears here. And I'm going to choose the aluminum alloy that appears in this tree that pops up. So now that we've assigned the material as aluminum, we can go ahead and build the mesh for this analysis. I'm going to go ahead and generate the default mesh by right-clicking on Mesh and pressing on Generate Mesh. And as we can see, a mesh has been created that is fairly coarse, but is very orthogonal. Now, if the mesh was too coarse for our liking, we could also refine it and make the elements smaller. So in order to do that, we can press right-click on Mesh, go to Insert, and insert a sizing. So as we can see, we have a question mark beside sizing, and this is because we have two yellow fields here, which require user input for Ansys to use the sizing correctly. The first thing that we need to specify is the geometry, and the second thing that we need to specify is the type of sizing that we want to do. So for geometry, I'm going to go ahead and press on the body selector command over here. And I'm going to select my body. As we can see, it's highlighted now. And so now I'm going to go press on no selection, and I'll press on the apply button that has appeared. And we can see that one body has been specified for our geometry for this body sizing. By default, we can see that the element sizes have been initialized as 0.070666 repeating meters. And this was seen to be very coarse, so we can go ahead and put in a smaller number for our element size, which will act as our maximum element size for this mesh. So I'm going to specify my element size as 0.025, which is smaller than 0.07. Now with this information specified, we see that we have a check mark beside body sizing, but now we have a lightning bolt beside mesh, and this is because now we've added something to our mesh, so we have to update our mesh. So in order to do that, I'm going to right-click on mesh, and I'm going to press on update. And as we can see, the mesh has updated and is a lot more finer elements now, but still has the same orthogonality as before. So this mesh should not be a problem for the analysis that we're going to do. Now with our mesh created, we will go ahead and specify our boundary conditions. As we can see, we have a question mark beside steady state thermal, and this is because we are missing our boundary conditions for this problem. As stated in this problem statement, we want to specify the right-hand boundary to have a temperature of 50 degrees Celsius, and we want the left-hand boundary to have a temperature of 22 degrees Celsius. So in order to do that, I'm going to go ahead and right click on steady state thermal. I'm going to go to insert and I'm going to insert a temperature. Now we can see that the details of temperature here are asking us to describe what geometry we want to apply it to and what the magnitude of temperature is going to be. So I'm going to go ahead for geometry. I'm going to use the face selector tool beside the body selector tool up here, or we could use Control F. And I'm going to click the surface that I want to apply this temperature to, being the left face of our geometry. I'm going to go ahead and press apply to apply this selection to the temperature. So we can see that one face, the left-hand face, has now been added to our geometry of our temperature. And we can see that the magnitude by default is set to room temperature or 22 degrees Celsius. So that is good to go. Now I'm going to do the same thing for the right-hand boundary to apply the 50 degrees Celsius. I'm going to right-click on steady state thermal. I'm going to go to insert, go to temperature. Using the face selector tool, I'm going to choose the right face. I'll press apply on geometry. So we can see that one face has been applied to our geometry for temperature 2. And now we're going to specify the second temperature as 50 degrees Celsius. And that is it for our boundary conditions. So now we can go ahead and choose what results we want to see from Ansys and run the simulation to get the results that we want. So in order to specify some results, I'm going to go ahead and right-click on solution. I'll go to insert, go to thermal, and I'll insert the temperature. And this will allow us to create a temperature log, or for Ansys to calculate the temperature along all the nodes of the mesh, and we'll be able to display the temperature at all the nodes on the screen. So now with this specified, we can go ahead and run the simulation. To do that, we're going to go ahead and right-click on steady state thermal, and we're going to press on solve. And because our mesh is very orthogonal, and this is a very simple analysis, it should not take too long for this analysis to run. Now that the solution has compiled, we can go ahead and view the results that we've obtained. So if we go ahead and press on temperature, we can now see our temperature gradient throughout the plate. And as we can see from the color bar on the left-hand side here, we can see that our boundary conditions are being respected. The left-hand side is staying at a temperature of 20 degrees Celsius, and the right-hand boundary is being steady at 50 degrees Celsius. And then we can see the temperature gradient throughout the plate. It might be a little easier if I deselect the elements here. So if I go to edges here and press on no wireframe, now we can really see the temperature gradient throughout this plate. Knowing that our boundary conditions have been respected, we can say that the results that we have obtained are fairly good. But in order to further validate the results that we got, we can recall that from the slides, we could use the parameters that we specified in the problem statement and plug them into Fourier's law in order to get the total heat transferred through the plate. And using Ansys, we can go ahead and show what the total heat transfer through the plate is for the analysis that we initialized here. So to do this, I'm going to go ahead and select the two temperatures by pressing on temperature and holding control and pressing on temperature 2. And I'm going to drag this into the solution. And as we can see, there has been two reaction probes that have been created. And in this case, this is going to specify what the total heat transfer through the plate is. As we can see, we have a lightning bolt, so we need to reanalyze the simulation. So to do that, I'm going to go ahead and right-click on solution and press on evaluate all results. And now we have check marks beside the reaction probes. So we can press on the reaction probe. And for the first one, we can see that this is specifying the reaction through the left-hand plane. And from the tabular data down here, we can see that the reaction is negative 42,435 watts. If we press on the reaction probe 2, which specifies the reaction on the right-hand plane, we can see that the tabular data gives us a total heat transfer to that plane of 42,435 watts, which is exactly consistent with the results that we calculated using Fourier's law. And now you may ask why one of the reaction probes was showing a negative number and the other one was showing a positive number. And this is due to the heat flow or the temperature gradient that was created through the plate. So the heat is being transferred from the high temperature to the low temperature area. With the results validation performed, we can go ahead and say that the results that we've attained from the simulation are acceptable. So there you have it. This is how to create a steady state thermal analysis of conduction through a solid plate. I hope this video was helpful for you guys. Don't forget to leave it a like if it was, and subscribe for more engineering content.